Hey there, I'm Infixter, and welcome to Shenzhen I. This is a puzzle game where you solve the puzzles by creating little devices and programming them to perform certain tasks. So I haven't actually played any of this game myself. I have watched a Let's Look At video on it, so I'm familiar with what we'll be doing, but I haven't actually played anything yet. But what I have done is familiarize myself with the manual that's provided with this game, and so you'll see this little button here. It says datasheet, and what that does is pop up a PDF manual that describes the little devices we'll be using, the microcontrollers that we'll be using to create the device, and the little programming language we'll be using to control it and perform whatever the tasks we get are. I should also probably mention that I am a computer scientist by trade, so I do programming all the time. This programming will be different. It's more low-level, more assembly-like programming. And if you have no idea what I mean by that, don't worry. You'll kind of see what sort of program we'll get in there. So I expect I'll be able to pick up this game relatively quickly. But I think as the game goes on, the puzzles will get more and more challenging. So hopefully that ends up being the case, and I'll have some interesting challenges ahead. So like I said, before I started recording, I did review the datasheet, and I might refer back to that from time to time to look at the instructions and see how different pieces work. It also has a little bit of the story in the datasheet, and the basic story is that your character is an engineer who is unable to find work in his or her own country, and so we move to Shenzhen, China to work for a company there to create devices. So I think that's about it for the intro, the story. And so the main way we play this game is by going into our email and getting tasks from our boss. These other emails in here are just some kind of welcome emails, like the CEO of the company emails you and gives you some welcome information. Some other coworkers and your boss emails you to sort of just say hello and things like that, give you some atmosphere for the game. And of course, one of your coworkers tells you should read the manual. So of course, that's what I did. So our first task in this game then, and where we'll be starting playing, is to create a little fake surveillance camera device. So let's read this email here. Security camera fake from our boss. So this product is an imitation mock security camera. It has two blinking lights. The first light blinks in a regular pattern, and the second in an intermittent light. So it should be blinking in a more random intermittent pattern to resemble data upload. As you'll notice, the design is partially complete already. A previous engineer quit before finishing the assignment. Note the timing diagram in the verification tab. When you simulate, your output should match those expected values as indicated. Let the simulation run until it passes all of the test cases to make sure you have a proper solution. And so this guy here then is just a coworker and says, I'm absolutely certain you'll be better than the last person. So it's great. So our objective is to create a working design for this product. So let's go ahead and jump into the CAD concept. So yeah, this is where we actually created a design. Whoops, I didn't want to do that. Let's go ahead and delete that one that I accidentally created. So new design 1, version not yet verified. So let's go ahead and open the design. So it looks like we have one little microcontroller already in here that does some stuff. Let's see how these controls work here. So our information. So we have an active and network are simple outputs connected to LEDs. Okay. So these are two little outputs that are connected to LEDs, and so that's what we do. So active is just that light that we want to blink intermittently, and network is that light that we want to manually blink. So control the active network outputs with fixed and repeating patterns as indicated in the verification tab. So if we go to the verification tab, then we can see two little lights. And so this is what we want our device to do. Here we can see kind of a model of our device. We've got the two lights on it. And so when we run it, we want the active light to first be off. That's what this is indicating here. And then we want it to turn on. And then we want it to go off. Then we want it to go on, off, etc. In a sort of very fixed pattern. So network, our network light, then we want to be more intermittent. So it's not quite random. There is sort of a pattern, but it looks sort of a little bit more random. It's not as regular as the other pattern. So what we can do is we can simulate what's going to happen when we just run the device. So you can see the active light appears to work. It's off for a while, on for a while, off for a while, on for a while. Whereas the network light just stays off the whole time, probably because we haven't connected anything to it yet. That's sort of how you can run the program and see what happens. And we get some information about our thing here, like how much it costs to produce, how much power we're using, how many lines of code we have. And you can also sort of step through time steps one by one if you need to help you sort of fix this out. I'm not sure what step versus advanced is, but I'm not going to worry about it. So let's go ahead and look at the first little thing here, and I can sort of explain what's going on. So we've got move, sleep, move, sleep. That's what these commands stand for. And so what we're going to do is move the value of 0, which indicates off in this case, to P0, which is one of our outputs. So we're going to move 0 to P0. Then we're going to sleep for 6 time units. So we're going to sleep for 1, 2, 3, 4, 5, 6 time units. Then we're going to move 100 to P0 to switch the light on, which is going to jump us up here. And then we're going to sleep for another 6 units. And the whole thing's going to repeat again. So that works as is. So now let's try to get the network light to work. So in this case, we want to go ahead and start by moving 0 to P0. And it'd probably help if I connected the output there. That's appropriate. So move 0 to P0. So that'll just set the device off. And then it looks like we sleep for 1, 2, 3, 4 units. So sleep 4. And then we're going to move 100 to P0 to turn it on. And then we're going to sleep for 1, 2 it looks like. So sleep 2. And we're going to turn it off again. So move 0, P0, off. Then we're going to just sleep for 1 time unit. And then we're going to turn it on again, move 100 P0, oops, 100 P0. Oops, invalid instruction, typo. And then we're going to sleep for another 1 unit. And then that's it, we're done. We'll move because then it'll restart and turn it off again. So let's see if I actually did that right. So if we simulate, see down here in our tab, our device passes. All right, you've successfully completed 1 test run. Let the simulation continue running to complete the verification process. All right, and it looks like we did it. So what's kind of cool is when you finish the device, it compares your results to others that people have created. So here's our production cost, and you can see we're right in the middle of this 6 unit range. You can also show how much power you're using, and so you can see that some people have managed to use less power than us. You can also see the number of lines of code, so some people have managed to do this in very, very few lines of code. So that's pretty cool. For now, I'm going to go ahead and move on. Maybe we'll come back and try to optimize this later, but you can see we're right in the middle for everything. And I think as you progress in this game, you get access to more sophisticated microcontrollers that might allow you to do things in fewer steps. And so we can come back later in the game perhaps and try to accomplish this using maybe less power or less production costs or in fewer lines of code. But for now, let's go ahead and return to the email and see what happens. We get email back. Thanks for your prompt work on the blinking lights. Looks okay. All right. Looks like first puzzle complete. So let's see what's next. Shenzhen Days. Why are we even here? Shenzhen Days. Why are we even here? From a coworker. Hi everyone. We've had a bunch of new signups this week, so let me reintroduce myself. I'm your host, Lily Liu, and I run this fun little mailing list for expats in Shenzhen. I'm here to demystify some aspects of life and culture here, along with side help of color commentary. Sometimes just the color commentary. Yeah, I get distracted. Alrighty then. Today's topic is, why the heck are we in Shenzhen? No, really, like, why the heck are we all here at all? I may be throwing in some words there just for fun. I'm going to add my own little color commentary to this as well. How's that? I don't mean in the immediate sense. Sure, we all have some job or some businessy thing to do, but let's talk about the larger factors at play. We're here because Shenzhen's been one of the fastest growing cities in the world for the past few decades, ever since it was declared a special economic zone back in 1980. Oh, I should also mention that this game takes place in the future, and so 1980 is a while ago. Does it actually say where the time? I think it says somewhere where what time we take place in or what the year is, but I'm not gonna worry about that for now. Anyways, back to this email. We're here because it, and really the entire Pearl River Delta region, is sprawling megacity, wholly dedicated to trade, manufacturing, and services. A giant economic machine. We're here because what's possible in Shenzhen really isn't possible in many other places around the world, certainly not in the same scale and cost. So where's all this capability headed, in the future? Are we going to just make more stuff, more products and things until the world is buried in crap? I guess I'm asking, what is all of this incredible growth for anyway? I have some ideas, but that's the topic for another day. Yours, Tilly. Interesting. So I wonder if this story is going to kind of build somewhere, maybe be some sort of social commentary on why we're building a bunch of stuff. Anyways, I guess we'll just see where the story goes from here. There was something else I wanted to mention. Oh, that's it. I don't know if I'm pronouncing this right. Shenzhen. I may be mispronouncing that. I may switch pronunciations along the way, so if I am butchering the pronunciation of this city, I do apologize. But for now, let's see what our next puzzle is. I think that's what these exclamation points means. It's an unsolved puzzle. Replacement factory module from our boss. Our factory floor has some examples of older equipment that requires control signals to be amplified. We had a device that adjusts signals for this type of machine, but recently it was broken, smashed. This is an appropriate project to teach you about inputs. So from our little mentor guy, I guess, Carl. Smashed, hang on a sec, what happened? Is everyone okay? No need to worry. That seems a little suspicious that he's kind of worried about things getting smashed. But let's not worry about that for now, and let's go ahead and jump into our design software. Here's a copyright 2026. Maybe that's the year that we're in. So new design 1, not yet verified. So let's go ahead and hop into it. So it looks like we have a control input and a control output here. And according to the information, control in is a simple input connected to factory equipment. Control out is a simple output connected to other factory equipment. Oddly specific there. The signal from control in should be multiplied by 2 and copied to control out. All right. So verification, we've got some incoming signal. We want to multiply it by 2 and send it to control out. Cool. Should be easy enough, I hope. Let's go ahead and get our little microcontroller. We'll wire up the inputs to P0 and the outputs to P1. Now I am going to tab over briefly. I don't think I have it set up for you to see this, but I just tabbed over to the reference manual, and I just want to check some instructions here to make sure I know the appropriate commands we're going to be using here. Because there are some arithmetic things like multiply and stuff. All right, cool. So I think what we want to do first is we're going to take the value from the input and we're going to move it to this thing called ACC. I'm probably going to call this accumulator because I think that's what it stands for in this context. I'm not 100% sure, but we're going to move it to the accumulator, and this is a register, basically a place where we can store some data and manipulate it. So we're going to move P0 to ACC, so that'll take whatever data we have coming in from the control line, move it to here. Now we want to multiply it by 2. So there is a multiply instruction, so mul 2. And what's kind of a little funky is you might be asking, what am I multiplying by 2? Well, we're multiplying the value in ACC by 2. That's basically all we're doing. We don't get to specify what the other value is, we just specify what we want to multiply by, and whatever's in ACC is what gets multiplied by 2. So once we've done that, then we can take ACC and move it to P1 to send it to output. I have a bad feeling like I'm missing something here, but let's go ahead and just test what we've got. Part not sleeping. Okay. So I guess we just, at the end of this, reset. At the end of this, we just need to sleep 1. Let's see. Yeah, that's what we just need to do. Okay, we just need to make sure that we're only doing, we're sleeping for 1. So this little thing seems relatively straightforward. We'll just go ahead and let this continue doing its test run. Oh, cool. Once it does 4, it like jumps to 80. Huh. All right, so we've completed this task, and again, according to these graphs, we're pretty much right in the middle of everything, and our production cost is 3. Power usage is 240. Some very few people were able to get less than that, and our lines of code is pretty much right in that range of everybody else's as well. Yeah, I'm really curious about these people who were able to do it and fewer did, so I might be curious to come back and explore at some point. But anyways, let's see. Looks good, thank you. Take care, yeah? All right, sweet. So that does it for our second puzzle. So far, so good, as far as I can tell. I'm having fun. All right, let's see what the next thing is. Please enjoy a game. My daughter is learning programming. She created a simple card game. Would anyone like to try it? Try and give her some feedback for her. I put a link on everyone's desktop. She is interested in becoming a game developer. Wow, Jay, that is both a lot more polished and far harder than I was expecting. Your daughter's managed to design quite the interesting patience game. Maybe there could be an undo function. She says she doesn't think she needs an undo function because it's actually quite easy once she develops some skill. She really takes that view. Objective: win a game of solitaire. Game of solitaire. Oh, we have solitaire on our thing now. Cool. I think I might skip this for now because I don't think you guys want to really watch me play solitaire at the moment. So we'll come back to this challenge a bit later, and if you're not familiar with what solitaire is, well, it's basically just a solo card game that you can play. So we'll come back to that later. Let's move on. All the parts. Now that you're up and running, I figure it's safe to let you use all of the lovely parts we have available to us. Just be warned that not all of them are going to be useful for what you're doing immediately. On you go then, Carl. Okay, so I guess we just got access to more of the different devices and microcontrollers we have. I've only really familiarized myself with that first one, the simple one, the MC4000 that we've been using. I know there's also, I'm cheating, I'm using the little reference manual. There's also an MC6000, which has some extra sort of features and things. And beyond that, I have no clue because I haven't looked at them at all. And the Let's Play video I watched didn't go past those two either. So I don't know if we just got access to everything. It does say all the parts. I hope it doesn't just try to throw everything at you. I hope it sort of gradually introduces you to the rest of the parts. But if it did throw everything at us, well, we'll see what happens. So let's see what our next task is, the pulse generator. In order to test some of our new manufacturing equipment, we need a pulse generator with certain requirements, specifications. However, instead of buying one at market price, I thought we could simply create our own. For this project, we'll need to make use of conditional execution. Please continue your study of the language reference. All right, so let's open this up. And if you're not familiar with what conditional execution is, well, I'll explain that as we go. All right, let's see what we got here. So it looks like we have two things. We have a button and a pulse. Button is a simple input connected to a button. Pulse is a simple output connected to an electronic device. When the button is pushed, generate pulses as indicated in the verifications tab until button is released. Okay. Cool, so I guess here's what the button is pressed, and we want to do things while the button is pressed. Oh, it looks like we do have access to a lot of other stuff. Note was note. Oh, I guess it's just like we can just take. Oh, okay, it's probably just for writing comments so we can describe what our code's doing. Okay, so yeah, it looks like we do have access to everything, but it says part not recommended, so I'm not going to mess with those for now. I think I'm going to just go ahead and start with our regular simple microcontroller that we've been using, the trusty old MC4000. So let's wire up the button to P0 and this to P1. It looks like we sort of have discrete intervals here. And basically, when the button's pressed, we want to alternate the light to be on and then off every one time unit. I might just say 1 second to be easier. So every 1 second, But then when we release the button, we want it to go back off for sure. So I think what we want to do at the beginning of every step here is go ahead and move P0 into ACC. I'm going to check the reference manual here really quick, because there are conditional instructions that basically say if some value is greater than or less than or equal to some other value, to then execute certain instructions versus not. So it looks like we can, maybe we don't actually have to put it into ACC to do this. So I think what I want to go ahead and do is first of all, let's just kind of do this. So if the button presses, we get the value of 100. So test equals P0 100. So this is basically saying if P0 is equal to 100, and plus means do that instruction if that condition is met, and minus means don't. So right now we're going to do plus. So if the button is pressed, well, obviously if the button is pressed, we want to turn the light on, and then we want to wait a second and turn the light off. So if the button is pressed, let's go ahead and move 100 to P0. So turn on P0, sleep 1 second, move 0 to P0. If the button is not pressed, move 0 to P0. Is that a minus sign? Minus. What if I did that right? Let me just write this line again here. Minus, yeah, move 0 P0. I don't think that's gonna work. Let's just see what happens. Nothing, okay, right. So if the button is not pressed, we want to move that and sleep 1. Alright, let's see what that works. That didn't work. Why didn't that work? So here we should be doing a test equals, and we're going to see that the button is pressed. So we're going to move 100 to, oh, okay, right, not P0. We want to move 100 to P1, which is our output, not P0, P1, P1. Okay, now let's simulate. Ah, why didn't we turn it off? So I'm going to go ahead and just step through it. Oh, okay, I see. So, real quick for reference, step means we're going to step through each line of code individually. Advanced means we're going to advance through the next time step. So if I reset it, if I just do step, we're just walking through the code one step at a time. But if I say advance, we just advance to the next time step down here. So let's advance to when things changed, when the button is pressed. Now let's go ahead and step through the code. So we step through, we're going to move 100 to P1. So we've turned on the light. We're going to sleep for a second, and then we're going to move 0 to P1. So we're going to turn off the light. Oh, you know what? I forgot to sleep there. So we need to sleep at the end of this. So no matter what, we're gonna, okay, I'll do a little bit of a thing here. We're gonna sleep 1 at the end of this. But if we notice at the end of both of these conditionals, both here and here, we have a sleep 1. So what we can do, a little programming trick, is instead of doing it in both places, let's just delete the minus and say sleep 1. So we're going to sleep 1 no matter what at the end. All right, so let's try running it again. There we go. That looks better. All right, we passed the first of, well, 80 tests, but really only 4 because the last 76 go by really quick if you've passed the first 4. All right, we did it. But we didn't do it very well. Production costs, pretty low, which is the normal thing. Our power usage and our lines of code are inoptimal, though. We're using more power than some people, and we're also using more lines of code. So it looks like the average is about 5 lines of code. And the average power usage is a little bit less. I'm going to take one more quick look at this because I'm curious if we can make this more efficient somehow. You know what? Here's another little thing that I should have picked up on. See how on both conditionals, both the plus side and the minus side, we're moving 0 to P1 at the end. That means we can do that instruction no matter what. So again, we can do the same thing we did with sleep here. We can just delete out the minus sign and delete it out from both sides and basically have it happen no matter what. So let's go ahead and simulate again. Make sure things still work. Looks good so far. So this should drop our power usage and our number of lines of code. There we go. Now we're with the big chunk. Oh, but we're still using more power than most people. Interesting. I'm going to take one more look at this. We have a sleep one here and a sleep one here, but how can we use less power? You know, I'm not really sure how power usage is calculated. Let's see how much power like each of these steps take. So oh wait, reset. So looks like each line here, that equal used 1 bit of power. This move uses 1 bit of power. I'm looking down here, I'm pointing at my screen like you can see that. So we've got the different instruction highlighted to see which one we're on now. So we've used 2 units of power, 1 for the test, 1 for this move. And sleep also uses 1 power, so we should have that a few times, just 6, 9, and now we've actually had something change. So how much power do we use when something changes? So the test is going to be 1. Move should also, I think, just be 1, so we should be at 11, and then 12, and then we've got to move to 0 again, and then sleep again. Yeah, I'm not really sure, but I think I'm not going to worry about it. You know, we do have, does this do anything? Well, what does this do? Does that increase the speed? Oh, it does. Neat. Okay, so I'm going to jack up the speed since we're just going to quickly verify everything. Yeah, so we do have a solution. We're using a little bit more power than the average, but still not bad. Again, we can maybe come back and look at this one again sometime in the future, but for now, we'll go ahead and move on to the next one. Pulse generator. Yes, looks okay. Suitable for our purpose. Great. How much time have we been recording? So we're coming out about the half-hour mark, so maybe I'll go ahead and do one more puzzle and call it for this video. So let's see what our email says. Take an orbital selfie. Trips start at just our 89999. Dear adventurer, experience this star and Earth as you have never seen them before. Enjoy a surprise and delight of true weightlessness. And of course, take pictures of yourself that nobody will soon forget. Did you know that there have never been a better time to take a trip into low Earth orbit? Demand is skyrocketing, and prices are cheaper than ever. Wait, demand is skyrocketing and prices are cheaper. That's usually not how that works, but okay. Now is the time to get in on this trend, which has been popularized by international superstar Cool Dad and many other Cool Dad. Oh my gosh, this is funny. Tickets are going fast. JSC Space Adventures Moscow. Well, that could be fun. Maybe a little hint at the story. Who knows? All right, so what's our next thing? Looks like we have 2 sort of options here, but let's just go with the first one, do it in order. Light up signs. It begins. I got us an incredible deal with a major esports personality, the Solid Steel Gamer. Her team's contracted us to make light up signs that actually animate for her fans. As long as we can keep the cost down, they're going to want tons of these things to hand out at matches. Looks simple. Just add just a few states. All right, so let's check this out. Cool. So this is the other one that I remember the Let's Player, or not the Let's Play, the Let's Look At video I watched do this one. But I don't remember how he solved it, and I also do remember that it wasn't a very elegant solution, so I'm hoping to come up with something a little bit better. So we got here, click 0 and click 1 are simple outputs connected to display segments corresponding to a clicking animation. During 0, 1, and 2 are simple outputs connected to a display segments corresponding to a drinking animation. Control the display segments with fixed repeating signals as indicated in the verifications tab. Alright, so bunch of outputs, and what this is going to end up doing is lighting up different portions of the sign to have different sort of animations. And so you're going to see this little finger clicking, and you're going to see the gamer take some drinks from her presumably sponsored energy drink of choice. Alright, so our click signal here seems pretty easy to do. So let's go ahead and throw in a simple thing here. Let's go ahead and just wire up P0 to click 0 and P1 to click 1. And I think what we can just do is... Okay, I think I'm going to just go for a simple solution for this at first, but then I'm going to come up with something a little bit more clever. I have an idea for this one, but let's just go with the simple solution first. So move 100 to P0 to light up the click 0, and at the same time we're going to move 0 to P1 to turn that off, and then we're going to sleep for 1, and then we're going to do the opposite. So we're going to move 100. Sorry, we're going to move 0 to P0, move 100 to P1. So you can see this is kind of the opposite of what we just wrote. And I might go ahead and line these up a little bit so it's easier to read. Oh, and then of course we're going to sleep 1 again. So let's go ahead and drop the speed down and simulate that. So we can see our clicks, they're looking pretty good. They're just doing the right thing. Perfect. Now what was the clever thing I was going to do? I think there's a not instruction in here. I have to see how it works. Yeah, let me look at this manual for a quick second here to see if I can come up with something a little more clever. And if it's not coming quickly, I'll just go ahead and move on to the rest of this task instead of getting bogged down here for too much. The value, okay, so not is, if the value in ACC is 0, store the value of 100 in ACC, otherwise store a value of 0 in ACC. Can I use that to make a more clever sort of thing here? Okay, I'm just going to leave this here for now, and I'm going to reset the simulation. Can I move this? No, I do not want this wire. How do I, oh, right click, okay, deletes wires. So let's connect it up to this one for now, and I'll, oh, it's not going to be easy, is it? Is it? Oh, can I move this? Yeah, there we go. All right, we're just gonna move that out of the way. Wire up the other one. See if I can do this. So I think what I want to do is move ACC to P1. It's got a 0, so on the first sort of section, it's going to correspond to a 0 in P1. And then we're going to say not. And then we're going to move ACC to P0. And then we're going to sleep for 1. So what it's going to do is it's going to move the value of ACC to P, I have a typo, to P1. So it's going to move the 0 to P1, which is what we want it to be off. And then it's going to negate it. So it's going to take this 0 and it's going to make it a 100. Because how the not works, I'm reading from the manual here, it says, if the value in ACC is 0, store a value of 100 in ACC. Otherwise, store a value of 0 in ACC. So it's got a 0, so it's going to become 100. And then we're going to move it to P0, which will turn on click 0. And then we're going to sleep for 1 second. And then after that, we're going to move ACC to P0. So now at that point, ACC will have a 100 in it, meaning that we're going to turn on click 0. And then we're going to negate it again with not, and then we're going to move it. So let's actually go ahead and just get rid of this, and we can step through and I'll show you exactly what's going to happen here. So at the beginning, ACC has 0, so we're going to move that to P0. We're going to turn that into a 100 and then move it to P0. I'm going to sleep. See, we've got it. Now we're going to kind of basically do the opposite. I'm going to turn that one on, switch it again back to 0, turn that one off, move on. So if I just simulate this, this will work, and it's just a little bit more clever than the other one. It's fewer lines of code, going to use less power. Cool, power usage 84. What was our other one's power usage? 184. You know what? I'm curious. It's unfortunate that I can't save it, but I'm just going to go ahead and retype everything. So 184. Let me go ahead and write that down. 184 is our current power usage. So let's do the other version. So move 100 P0. Move 0 P1. Sleep 1. And we're going to do the opposite. Move 100 P1. Move 0 P0. Sleep 1. So simulate. Yeah, that's going to use a lot more power, I think. 184 versus... Wait, how does that use less? 138. Strange. Yeah, I don't really know why that uses less power for the same set here. If we step through, 1 unit of power, 1 unit of power, 1 unit of power. Sleeping also uses 1, right? Yeah, so that's just... Each iteration uses 3. Sorry, 6. 1, 2, 3, 4, 5, 6. Oh, you know what? I bet I know what it is. So this one we have 6 instructions, gets us through 2 time steps, right? We've got this time slice and this time slice taken care of in 6 instructions. Whereas with our other way, since we only had 1 sleep in there, we used 1 time slice was actually 4 instructions instead of 3, right? So this 3 gets us to the first time slice, this 3 gets us to the second time slice. With our other way, we had 4 instructions total. That got us through only 1 time slice. So I'll just, for the sake of comparison, move ACC P1, not ACC, sorry, just not, move ACC P0, sleep 1. See, that's 4 instructions, but that only gets us through 1 time slice. So we have 1 more instruction per time slice than we did with the other method. Okay, well, I attempted to be clever. I'm a little bit clever in terms of having fewer lines of code, but it uses more power, and I think that's a bigger downside. So, so let's go ahead and not do that. And I am going to just be a little bit neurotic here and move this closer. Okay, maybe not. And move this closer here so it's nice and neat in this little corner. But not that close because I do need to be able to connect the wires. So let's move it over just a hair and connect up the inputs and outputs. And we'll go back to the other method, which I conveniently copied onto my clipboard. So let's go ahead and simulate. We'll see that our click input and output is done. Cool. So now for the harder part, the drink thing, drink animation. And I think I'm going to check out this bigger MC6000 controller because this one actually has 3. Does it have 3? No, it only has 2 outputs, P0, P1. Well, that's unfortunate. Well, it still only has 2. I think I'm going to go ahead and just use the regular good old MC4000 for this. So I do not want those to be connected. Although that might be interesting. I didn't know you could actually do that. I wonder how that works. So let's go ahead and connect P0 to drink 0, P1 to drink... I'm really not good at placing these wires here. To drink 1. And then we'll get another controller for drink 2 when the time comes. Actually, you know what? Given how this looked, I'm actually going to have this controller be for drink 1 and 2. Probably need to move it over a little bit. Let's do drink 0 first. That'll be a little bit easier. So drink 0 first. So for drink 0, what we need to do is turn it on. So move 100P0, sleep for 6, and then move 0P0 and sleep for 4, I think. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and then we'll restart. So let's go ahead and simulate that. See, our drink 0 output is done. Cool. Now there might be more clever ways to do this, but I'm just going to sort of do what I find to be the straightforward solution, since I tried to be clever with this one and really didn't succeed in any meaningful way. So for this one, they both start out at 0. So let's go ahead and move 0P0, move 0P1, and we're going to sleep for 1, 2, 3, 4, 5, 6. So sleep for 6. And at that point we can move 100P0, sleep for 1, because that's only on for 1 unit, move 0P0. At the same time, we move 100P1. So when we turn this one off, we turn this one on, and then we sleep for 1, 2 units. Sleep for 2. This might be trouble if we run out of space here. Sleep for 2, and then we okay. Let's actually not start with these because we're going to start by them being off. So we're going to sleep for 6, we're going to turn on P0, we're going to sleep for 1, we're going to turn it off at the same time that we turn on drink 2. Then we're going to sleep for 2 with both of them, well, with drink 1 off and drink 2 on. And then at this point we're going to move 0 to P1. So we're going to turn off drink 2. And I'm going to put this head, so we're going to move 1, P1. We're still not going to have enough room. I may have to use the bigger controller just for that. Unless I can combine drink 0 and drink 1 together. Which I think I can do. So let's try that. I'll maybe do drink 2 on its own. I'm going to try to combine drink 0 and drink 1 together. So move 100 P0. That's fine, and this one will be off at the same time. So let's go ahead and move 0 to P1. I'll connect that up later. Sleep for 6, okay. And then when I move 0 to P0, I'm also going to move 100 to P1. But instead of sleeping for 4, I think I'm still going to run out of space here. For 1, move 0 P1, sleep for 2, move 0, move 100 P1. Yeah, I'm like one instruction short. What does a bridge do? Look that up really quick. Is this even in the manual? I don't see it by that name. Well, I'll have to look up what this bridge does later. But I think for now what I'm going to do is just use a bigger board with more instructions. So we'll go ahead and revert this the way I had it. Sleep 4. And then we'll go back. Delete this out of here. We'll leave that as is. Let's go ahead and get rid of this, and we'll put this one on, and we'll wire up our inputs and outputs appropriately. Alright, move 0 P1, move 0 P2. Sorry, P0 and P1. Then we're going to sleep for 6. Then we're going to move 1 to P0, sleep for 1, move 0 P, sorry, not move 1, move 100. Move 0 P0, move 100 P1. So this is that point where we've turned off this one, but we've turned on this one. And then we're going to sleep for 2. And then we're going to swap again. So move 100 P0, move 0 P1. So now we're at this point. Then we're going to sleep for 1. And that should be it. And then we're going to turn them both off again and continue. So let's go ahead and simulate and see what this looks like here. So you can both watch this, and you can watch the little animation here, and you can see that our esports gamer is clicking and drinking appropriately. So looks like we solved this. There's probably a more elegant solution. Let's give in the norm here, production costs. Yeah, see, most people were able to do this a little bit cheaper. And I'd be curious as to how. They do it for 10 roughly, I guess, or maybe 9. So they're able to use a different piece here. Continue editing. Oh, I didn't notice. What is an MC4000X compared to a regular MC4000? Does that have an extra? I don't know. A lot more parts that it's showing up here, and it's not showing the whole not recommended thing. So anyways, there might be a more clever way to do this using some of these other parts that I haven't looked at yet, but I'm not going to worry about that. So we have indeed finish this goal. So let's go ahead and finish this out, and then I'll go ahead and end the video. All right. Yeah, so power usage right in the middle, length of code right in the middle. So there are better ways to do it, more clever ways to do it. But that'll do this one. Light up signs. Haha, the end result looks great. I love the way it looks like the solid steel gamer is really clicking the mouse button and drinking her soda. This is going to be huge. Great, so we made that task. And yeah, so that was a fun little first video of Shenzhen I. I'm having fun with this game. It's right up my alley as far as programming is concerned, and we haven't hit any major challenges yet, other than the ever-present challenge of trying to be too clever. I'm basically my own worst enemy, trying to be a little bit too clever in certain ways instead of just doing things straightforward way. Probably run into that problem again, at least once or twice more. But for now, thanks for watching the video. I hope it wasn't too dull. AKA, I hope you enjoyed it. Alright, thanks for watching. And until next time, have a nice day.